Hey guys, today we're going to have our second video about physics and calculus and how it all fits together, and our video today will be about integrals. So let me give you a little background using your previous physics knowledge here. Now our last video was all about derivatives, right? And it was all about how to find the function for velocity and acceleration from a displacement function. So we were taught last year that if this is your acceleration time graph, that this is your actual line, that if we were to find the area under this line, it would be acceleration times time, which would be our velocity. The second thing here, if we had a velocity time graph, we learned that the area under this curve is velocity times time, which is our displacement. And then we also had a displacement time graph, but we didn't really talk about area under a displacement time graph. So let's just focus on these two. So we learned in the last video that I could take dx dt from this graph and find my velocity, and then I could find dv dt and find my acceleration. But what happens if you wanted to go in reverse? Or what happens if your acceleration is not a constant number, but instead it's changing? So if your acceleration is a function, let's say your acceleration graph, instead of being a nice straight line, it looks something more like this. Well, finding the area under a curve like this would be a little bit difficult. We could do the classic method you guys probably like to do, which involves adding up little tiny rectangles and figuring out the area for all of those, and then I could add all those up, and that would be the area under the curve. Well, calculus has a really easy way to do that same thing for you, and it's called integration. When you find the integral of a function, you are essentially finding another function that describes the area under the curve. So when you integrate, you probably won't get a number. You will get instead another function that helps describe what's going on underneath here. So you can think of integration as the reverse of a derivative, or you are undoing a derivative, kind of, sort of. So if I had an acceleration time graph, the integral of my AT graph would give me my velocity function. And then if I wanted to take the integral of my velocity function, it would give me a function for my position. Now, in math, we denote integral with this kind of long S-looking symbol. And a lot of times there are limits placed on your integral, which I can talk about here in a second. But let's just talk about integrals in general now. So just like I taught you guys one derivative rule, I'm going to teach you one integral rule, and it's a power rule for integration, just like the derivative rule was a power rule. And it's the easiest integration rule you'll use, and the only one you need right now. But the integral power rule says you add 1 to the power, you don't subtract, right? We're going to do the opposite of everything we did in a derivative. So we're going to add 1 to the power, and then divide by the new power. So let's take a look and see how this works. So let's say my acceleration function, and then you also add your constant. We'll talk about that in a second. So let's say 5x squared is your acceleration function, and I want to integrate this, and I'm going to integrate it with respect to x, and that's going to become important later because that tells you what variable you're actually concerned with in the integration. So actually, let's not use x, let's use t, because that's a little bit more appropriate here for what we're doing with acceleration time graphs. So dt. So I'm going to, this dt means that I'm going to integrate this with respect to t. So I'm going to add 1 to the power, so that makes the new power of my time be 3. And then I'm going to divide it by the new power, which is 3. So this will be a function for my time, for my velocity. And then I can integrate that again with respect to time. And I get 5t to the 4th divided by 12. And this is a function for my position. So, yeah, so the next thing we can do here is we can talk about limits on your integrals. A lot of times you will see written numbers here to here, 0 to t, 0 to 6. Basically, they're telling you over what area of your curve or your graph you're looking to try to integrate. So if we come back up here, if we say this is 0, and let's say this is 6, well, if my limits on my integral are from 0 to 6, then that's saying I only really care about this area. If I put limits like 0 to infinity or 0 to t, t just represents any, or a generic function, I guess, for your answer, which is most of the time what we're doing. So, let's do an example using limits. Oh, and then always add your constant. Guys, I'm really bad, those of y'all that are in calculus, I'm really bad about remembering to add a constant. So, that's going to change some of what we just did. So, here, when I integrate this, 5t cubed over 3 plus some constant that I don't know what it is, but since we found velocity, we'll call it v naught, or initial velocity is what this constant will probably end up representing. So why did I add a constant? Okay, so let's do a little experiment. The integral of just a constant number, 5. Let's say we're going to integrate 5 with respect to t. Well, there's no t in this value, so that means essentially right now t is power of 0. But I have to add 1 to my power. So the integral of 5 dt would be t, 5t. Because if I add 1 to my power, that gives me t to the power of 1. So what that means is that if you always have to think like forwards and backwards. So if I took the derivative of this function, the derivative of this function should be 5t squared. Right? Because I'm going to do 5t times 5t to the squared, and then that 3 is going to come out here. The 3's will cancel out. So this will be 5t squared, and then the derivative of this, because it doesn't have a t in it, will just drop away and be 0. So in order to get from my velocity function to my acceleration function, and make it look correct, there has to be a constant here. Sometimes that constant is 0, a lot of the times it is. We don't know though, because we don't really know anything about this function. I didn't even draw the graph correctly, so we don't really know what's happening. So to be on the safe side, we want to add this constant value here. So that means that if I integrate this, so let's try that again. V integral 5t cubed over 3 plus v naught. So whenever you have addition and you're integrating, you just integrate each term separately, right? This guy will become this guy, 5t to the 4th over 12. And then this guy becomes v naught t. And all that is your position.